Good afternoon. My name is Tony Kang. I'm the President and CEO of S.Biomedics. So here's our forward-looking statement. Today, I'll give you the brief intro of our company, followed by explanation of one of our leading programs, TED-A9, which is a cell medicine for Parkinson's disease. So we are a cell medicine company focusing on regenerative medicine based in Korea. Our backbone is the two cell engineering platforms, and through the two technologies, we are currently developing 7 cell therapy programs. Out of the 7, 4 are currently under clinical trials, and 5 are targeting incurable diseases. We also have strong and protected IP portfolios. Lastly, we do have our own GMP facility to apply our programs to clinical transitions. We currently have 8 production lines, and we plan to expand 3 times by 2025. Through our technology and experience, we are now a listed company in Korean Stock Exchange. As mentioned, the backbone of our company are these 2 cell engineering platforms. Shown on left is our first technology, TED, which is a standardized cell differentiation technology, differentiating any sort of pluripotent stem cells to neural precursors, or in other words, NPCs. The key is that we can secure highly purified NPCs, and therefore giving us an easier access to target CNS diseases. On the right, FAX is our second platform technology that forms various cell types into spheroids. The key is that we first prime the cells, or in other words, we enhance cells' abilities, and we form the cells into uniform spheroids consistently. Basically, it is a spheroid formation technology with functionally enhanced cells. Programs derived from both technologies are now under clinical trials in Korea. Through 2 technologies, we are developing 7 programs, as I said, and out of the 7, 4 marked in red are currently under clinical trial, which includes Parkinson's disease, spinal cord injury, critical limb ischemia, and crow's feet. All of our programs are developed with leading medical institutes, including Samsung and Severance Medical Centers. We are also developing 2 cell-derived secretomes, which are expected to enter into development stage by 2025. What I want to emphasize is that we use various cell types and that we use different cell types for different diseases. So the cells we use are disease-oriented. In terms of our IP, we have a very solid and firm portfolio, giving us the competitive edge for our development and commercialization. We currently have 146 applied and 90 granted globally. Now let's get into intro of our leading program, TED-A9, which is a treatment for Parkinson's disease. Now here's the development scheme of our TED-A9. We believe that ESC-derived ventral midbrain DPC transplantation is a promising therapeutic strategy for Parkinson's disease. Therefore, we developed a robust clinical-grade differentiation protocol for ventral midbrain DPCs. We start by differentiating ESCs to MPC by using 2 small molecules, and once again, differentiating MPCs to ventral midbrain DPCs by using another 2 small molecules, which takes a total of 25 days. The final medicine is the ventral midbrain DPC, which is matured into dopamine neurons after administration into the brain. What is unique about our protocol is that we successfully achieved the final modulation of signaling pathways for neural induction and dorsal-ventral patterning by exclusively utilizing small molecules only, and carefully modifying their timing and concentration. So basically, unlike previously reported methods using recombinant proteins for differentiation, we are using only 4 small molecules to differentiate ESCs to ventral midbrain DPCs. Furthermore, in each phase of differentiation, we have seen appropriate markers expressing at a very high level, and I will get back to this issue as I explain in the presentation. And as a result, we have secured highly purified ventral midbrain DPC from ESC for the treatment of Parkinson's disease. Now, going back to what I said, our TED-A9 program begins with ESCs differentiating into MPCs, and this is where our platform technology comes into play. We are using 2 small molecules, which are SP and dorsomorphin, to differentiate ESCs to MPCs. Every pluripotent stem cells, including ESCs, have its own differentiation tendency, and they can differentiate into either ectoderm, mesoderm, endoderm, and trophoblast, all depending on the nature of the cell line. So what we do is by using SB and dorsomorphin, we are blocking all of the differentiation pathways so that it can only lead to ectoderm and even further to neuroectoderms only. And as a result, we have established a method to secure MPCs from ESCs at a very high yield. For example, let's say hypothetically that we have 5 different ESC cell lines. If you look at the left, depending on the cell line, the MPC differentiation yield will be different, some low and some high. This is because the differentiation tendency is all different as mentioned in the previous page. However, as you can see on the right, our technology TED can secure MPCs at a very high yield consistently. This allows more suitable conditions for medicine development, and in this case, gives us a basis for Parkinson's disease development. Once we have secured MPCs, we are once again using additional 2 chemical molecules to differentiate MPCs to ventral midbrain DPCs. DPCs that are secured under our optimized protocol expresses ventral midbrain DPC markers, which are Ingerald-1, FOXA2, LMX1A at all above 99%, which is the highest yield ever reported. The high expression of key markers demonstrates that we have secured purified, highly purified ventral midbrain DPCs. In terms of production, our culture method can facilitate large-scale production of ventral midbrain DPCs. Our assumption is that our method enables generation of 3 trillion DPCs from 1 master cell bank vial, which can be administered to a minimum of 250,000 patients in clinical setting. Next, the graph on the left shows how we explore the dose response of TED-A9 on behavior improvement in Parkinson's rats to understand the connection between cell dosage and functional recovery, and to obtain an insight into the appropriate cell dose for human trials. Our result indicates that elevating the cell dose led to an associated increase in the number of transplanted DA neurons within the graft. However, this increase did not cause a proportional enhancement in the motor function of the PD rats, implying that once the number of DA neurons in the graft reached a specific threshold, not all extra cells could further improve the behavior outcomes. The video on the right shows rat control model versus treated model. What I would like to emphasize is that after 16 weeks of treatment, the PET-CT showed that treated rat had a continuous release of dopamine. Now, comparing our TED-A9 to groups in US and Japan, we had the earliest behavior improvement in the in vivo studies. US group showed behavior improvement after 5 months, whereas Japan showed improvement after 4 months. In our case, behavior improvement was shown after 2 months. So through this comparison of data, we believe that we have secured more superior DPCs. We have seen a strong improvement in our primate studies. Here's the data on 6 marmosets. 6 marmosets were inserted with MPTPs, creating Parkinson's animal model. The increase of score represents the increase of Parkinson's behavior. The blue line represents 3 non-treated marmosets. As shown, there is no change in the score, and the 3 marmosets had no improvement on behavior. On the other hand, 3 treated marmosets in pink had a dramatic improvement from week 6. By week 28, they all returned to normal behavior, giving us the assumption that Parkinson's disease had been treated in these 3 treated marmosets. Through PET-CT, we have seen increase of dopamine activities up to 32 weeks after treatment. Unlike the control group, where there is no dopamine activity is continuously improved over time in our TED-A9 treated group. All right. So here's the video showing change of marmoset behavior. The above row represents non-treated marmosets, and the bottom row represents treated marmosets. The video shows behavior activities of 2, 4, 10 weeks after treatment. Looking at the top row, there's no change in the behavior. There's practically no movement, and the marmoset is shaking very tremendously. Looking at the treated model, which is the bottom row, there is a huge improvement in behavior from week 6. By week 10, you can see that the marmoset is returning to normal, moving around and jumping on the bar. Now, this video is a firm evidence that our TED-A9 had a huge impact on Parkinson's animal model. All right, here's another video showing marmoset climbing the ladder. The video shows behavior activity before treatment and 2, 4, 20 weeks after treatment. Before treatment, there is practically no movement. From week 6, we can see dramatic change climbing up the ladder. By week 20, the behavior has returned to normal. All in vivo toxicology, biodistribution, and tumor studies were conducted by a contracted CRO with GLP certification. The CRO was responsible for transplanting TET-A9 into the nude rats and performing histological, hematological analysis with tissues extracted from the animals. No tumor and toxic effect was observed. Also, TET-A9 administered to the striatum were strictly confined to the injected brain tissue for a prolonged period and unlikely to spread beyond the brain. Now, through concrete preclinical data over TET-A9, we have initiated clinical trial phase 1/2A in Korea. The total number of patients are 12, with 6 in low dosage and 6 in high dosage. To explain more in details, we have enrolled an initial cohort of 3 patients at a low dose to assess safety, including the evaluation of dose-limiting toxicities over a period of up to 3 months post-transplantation. There was no safety concerns within this time frame, so we enrolled additional 3 patients at a higher dose for evaluation over another 3 months period. Now, assuming that there are no safety issues, we will proceed with the clinical trial by adding 3 patients to both low dose and high dose groups. The trial participants must have been diagnosed with PD for a minimum of 5 years, have responded to dopamine medication, but are experiencing motor complications such as wear-off, freezing of gait, and dyskinesia, which are significantly affecting their daily functioning despite medication therapy. So out of totally 12 patients, we have currently administered up to 6 patients as of today, and so far we are expecting very promising results. Now, to summarize, we have secured highly purified ventral midbrain DPCs from ESC by using only 4 small molecules. The obtained DPCs express key ventral midbrain DPC markers, which are FOXA2, LMX1A, Ingerald1, and OTX2 at a yield of 99%, representing that we have secured very highly purified ventral midbrain DPCs. We also confirmed that the final product, TET-A9, does not contain undifferentiated ESCs. Furthermore, we further matured the DPCs for 4 weeks. The mature cells express NERM1, PTX3, and TH, which are expression of dopamine neurons. As a result, DPC is the final product which will be administered into the brain. Then the DPC will mature into DA neurons. And this is our strategy for Parkinson's disease. As mentioned, we have secured cell medicine by securing highly purified DPCs, applied the program in GMP settings for production, and secured exceptional in vivo results, both in efficacy and safety. Our phase 1/2A began this year, and we expect to have the final patient administered by February 2024. And thank you.